Hi, welcome to this video tutorial series on kinematics of mechanisms. This is part A. We'll be covering introduction and position analysis. My name is Dr. Rajiv Lochana G. Chittavadagi. I'm an assistant professor and vice chair in the Department of Mechanical Engineering, Amrita School of Engineering, Amrita Vishwavidyapeetham, Bangalore. And this tutorial series has been divided into 10 videos. So the first video will consist of my introduction and the tutorial series. Then we'll discuss about what is degree of freedom of a point in 2D and 3D space, and then we'll be covering rigid body degree of freedom in 2D and 3D space. A quick run through the other parts. So in video 2 we'll be looking at a software called GeoGebra. Then in video number 3 we'll be understanding what are kinematic pairs and how to find degree of freedom of a pair. Then we'll look at how to write GeoGebra programs such that we can visualize how a prismatic joint moves and also how a revolute joint moves. Then in video number 5 we will look at mechanisms in general. There's an equation known as Grubler's or Kutzbach equation, which can be used to find degree of freedom of a mechanism in 2D and 3D. Then we'll look at how to solve different problems on finding the degree of freedom of many planar and spatial mechanisms. Then we'll have a 4-bar mechanism, slider crank mechanism and double slider mechanism. All these inversions also will be studying in video number 7. In video number 8, how to write GeoGebra programs such that we'll be able to find out or animate standard planar mechanisms as well as the ones with single degree of freedom and also multiple degrees of freedom. Then finally in video number 9 we will look into MechAnalyzer software developed at IIT Delhi. I'm also one of its primary developers, and we'll understand how the software can be used to teach kinematics of mechanisms in the form of animation and plots. Finally, to conclude this subpart of the series, we'll also be understanding if a given mechanism is seen by a student or a teacher, how do you convert that into a problem, and then how do you implement that in GeoGebra or any other software for that matter. So let's deep dive. Okay, by the way, this is part A. Similarly, B, C, D, E are also planned. So that will comprise of velocity analysis, acceleration analysis, cams and gears, and maybe an introduction to Recordine software as well. So that will keep in the coming days. Okay, the way I'm going to place my tutorials or videos are, I'll be using this digitizer to write like a blackboard teaching, and whenever required we'll be moving over to GeoGebra or MechAnalyzer, so that way I'll be sharing my screen. Okay, so first and foremost we should understand what is DOF. That is the first topic we would like to see. DOF stands for degrees of freedom. Okay, so a formal definition I can give you, but let's look at some explanation. If I have a system, coordinate system in 2D, and if there is any point P, if I want you to draw the same point P in your notebook or graph book, I need to give you certain information, that is either px and py are the coordinates of the point P. If I give you that value, you will be able to write down the same information. Okay, so degree of freedom is basically it's a number of independent parameters required to represent a system. Okay, now this is basically, I'll just underline some of the keywords. It's a number. Okay, it could be 1 2 3 0 -1, and the independent is also an important word. Okay, now let us look at another example or variation of this. If I want the same point P but represented in a different manner. Okay, so how do we do that? One way is I can draw a line from the origin to that point P. So this particular length will be there, and what is the inclination of this line with respect to the positive x-axis in counterclockwise direction. Okay, so here if I give you this information theta and r, you'll also be able to locate that point P. So this will represent as polar coordinates. Again, degree of freedom is 2. If I give you the value of r and theta, you'll be able to locate a point P using polar coordinates. Now one word of caution is theta is always measured in counterclockwise or anti-clockwise direction from positive x-axis. So let's follow this convention because then our life will become easier. Now, can I also write the other two variables? Let's say I can write this as px and py. Possible, right? The same point P will have px, py, r and theta. So now what we should also understand is, can we have random values of px, py, r and theta? Can I have px equal to 2, py equal to 2, let's say r is equal to 5 and theta is equal to, let's say, 60 degrees? Is it possible to have this setup? No, it is not possible. That means if I finalize the values of px and py as 2 and 2, this r and theta cannot have random values. Okay, so that means there is another definition of degree of freedom that we can also say is as degree of freedom is total number of parameters minus number of constraints or constraint equations. Okay, what do we mean by this? Let's say this system itself. So what is the total number of parameters? There are 4 parameters. And how many constraint equations? Okay, let's learn it this way. We know that degree of freedom of this point P is going to be 2. So obviously I need 2 here. Now what are those 2? We'll try to understand. Sorry. Okay, so very quickly let me demonstrate this. If I give you the value of px and py are given, okay, now if you look at this right angle triangle, if px and py are given, will you be able to find the value of r? R will be square root of px square plus py square. Okay, so that is one constraint equation. Similarly, if I know the value of px and py, I can also find the value of theta. So if I use tan theta, then tan theta is py upon px. Okay, so this is equation number 2. So later on, if you want to find the value of theta, so there is something known as a tan, that is arctan, tan inverse in computer language programs. Py upon px can be obtained. However, there is some problem in this approach. In a sense, py px, if both are negative, the division will give you a positive number. So tan inverse, what you get, you will not be able to know whether it is in the first quadrant or third quadrant. Similarly, if one of them is negative, we don't know whether it is in the second quadrant or fourth quadrant. So that's why in most of the programming languages we'll have this form called a and 2, where we send both py and px as two parameters, and accordingly the angle is determined. Correct quadrant it will be known. Now imagine we give you the value of r and theta. So how do we find the value of px? So let me draw that triangle again. So I have r, I have theta. R is the hypotenuse, this is perpendicular. Px, py. From trigonometry you know that cos theta is px upon r, so px will become r cos theta. Similarly, sin theta is py upon r, so py will become r sin theta. So again r and theta is given, so you will be able to have equation, let's say 1 here for this, and equation 2. So these are the constraint equation. So what it means is these are dependent parameters. Dependent is a function of independent parameters. So that is what we have understood so far when it comes to degree of freedom of a point. Now why is it important? Obviously this form will be used in our kinematics of mechanisms also. So that is the reason why we have derived it. Okay. Now let us look at rigid body. What is a rigid body? A rigid body is something that does not deform under the action of any external force or internal force. Rigid body does not get deformed under the action of force. Okay, so I'm having this mobile phone. If I am putting some force, there could be small minute deformation, but if we assume that there is no deformation, so we can consider this as a rigid body. On the other hand, if I remove the cover, so you can see that when I apply force, this is getting deformed. So we should not assume this as a rigid body. Okay, so obviously in mechanisms we assume most of the links or parts of a mechanism. What is a mechanism I'll define later, but for now are assumed as rigid bodies. So it's an assumption. Obviously when you put force there is always some minute deformation. We'll ignore that for now. Okay, now again if I consider this as a rigid body, now if it is in a plane, so that means I want the rigid body to be in a plane. So you can see that I can move the rigid body like this. I can also move the rigid body in this manner, and I can also rotate in this manner. Okay, so that means when I do all this, the rigid body is not moving away from the plane on which it is located. So the same analogy I can put on this rigid body. If at all it has to remain in the same plane, I can translate along, let's say, x-axis. I can translate along y-axis, and I can also rotate about the z-axis. So degree of freedom, another definition what we can think of is it is number of independent motions possible in a system. Okay, So that means degree of freedom is 3 for a rigid body in 2D space. Okay, I hope this part is somewhat clear. Now let's look at if I have a rigid body, in 3D space. Okay, so if I have X, Y and Z, and if I have a rigid body in 3D space, so that means I can consume the same. So if I have rigid body in 3D space, that means I can translate along, let's say, X direction, along Y direction, along Z direction. So I have 3 translations possible. Okay, now I can also rotate about X direction like this. So that means I can do rotation in this manner. I can rotate about Y direction like this. So this is Y direction, and I can rotate about Z direction coming out of the plane towards the viewers. So this is, so degree of freedom for a rigid body in 3D space is 6 for a rigid body in 3D space. So that comprises of 3 translations and 3 rotations. Now, so you may be wondering why we went ahead with rigid body in 3D and not point in 3D. Okay, let's do that also. If I have a point X, Y, Z, and if there's a point P, so there are 2 ways of looking at degree of freedom now. One is how many coordinates are required to represent that point. Okay, so obviously you will require, if I project something like this, so this part will become Px till this is Py vertical and then Pz. So degree of freedom is 3. So one way of writing is I should know what is Px, Py, Pz. Another way of looking at degree of freedom is how many motions are possible. So that means I can translate along X, I can translate along Y, I can also translate along Z. So degree of freedom is also 3 when you look at 3 motions, translation along X, Y and Z. Okay, so we have covered very briefly what is the degree of freedom. There are 2 definitions, or rather 3 definitions we have looked at. So the first definition was number of independent parameters required to represent a system. The second definition was total number of parameters by minus number of constraint equation, and the third definition is number of independent motions possible in a system. So this is a very brief introduction of GeoGebra. Now, of degree of freedom. In the next video, we'll be looking at how to write simple programs to understand whatever we have done so far. So stay tuned. Thank you.